From 0 to 3, we got 9/2. From 0 to 4, we got 8. And there was an actual pattern, and that pattern was 1/2 x squared. Now, that pattern is not a coincidence. That pattern is the fact that this, let me circle it. This thing right here is the antiderivative of x. So the antiderivative is giving us the pattern that's telling us the area under the curve. It's kind of wild. So from here, we see that the antiderivative is related to finding areas under curves. So that's like huge, actually, because what that tells me is that we don't have to use geometry anymore. So I did see that some of you were still, using geometry, and some of you got really, really great approximations in your homework for those who did do the homework, right? But we don't have to do geometry anymore. We can now kind of use the fact that, hey, if I take the integral of something, all I need is the antiderivative. And from that antiderivative, I could get the area under a curve. So it's wild. So that is the basic juice of the theorem that I just showed you. It represents antiderivative. So you see the antiderivative being used to evaluate an integral. And down here, basically what I did is I tried to kind of apply it to that very same example we've been doing, except I replaced the upper number with b, and I found the antiderivative right here. Then I said, okay, so then that means I need to plug in b into my antiderivative. See the b is being plugged in. Minus, there's my minus. Plug in a, I see a being plugged into this antiderivative. So cool, I'm subtracting these two. But then what is a and what is b? That's when I go ahead and substitute what's known. In this case, my a was 0. There's your 0. The upper numbers, we're just going to call that b. Well, b squared divided by 2 minus 0 squared divided by 2, basically 0 divided by anything, that's going to go away. And you're just left over with the fact that the area of x, the integral of x, is basically whatever the upper limit value is, b squared divided by 2. So that was me connecting this theorem with the patterns that we were investigating the other day. So that was kind of the whole point. Now let's say that the A and B stuff right now for you is kind of going over your head. Like, oh, I don't know. Let's actually do some examples. That's where the examples help us. So and here was an example. So of course, if you look at this picture, if you look at this integral, so the integral from 1 to 3 of x dx, and I went ahead and I included the picture of the function y equals x. Now, of course, you can go in and use geometry, like, sure, you could totally do that. But when it comes to like curvy graphs, you actually cannot use geometry. That's going to be too much work for you to actually use geometry. And in addition, you'll only get an approximation and not the exact area. In this case, yeah, you can. It's a trapezoid, so you could get the perfect area. But I'm going to actually, instead of finding the area of this trapezoid, I'm going to be using the theorem, the shortcut. So this is basically the shortcut. So this is how we do the shortcut. Step 1, find the antiderivative of this. The antiderivative has the notation capital F. So how do I find the antiderivative? Let me remind you all. The antiderivative, how you find it, is basically this rule. X to the n plus 1 divided by n plus 1. Because this is just x, there's an imaginary 1. So you have x to the 1 plus 1. That's what gave me my 2 right here. And then you have divided by 1 plus 1. That's divided by 2. Well, that's the same thing as bringing this 1/2 to the front. So step 1, find your antiderivative of your function. Step 2, you're going to plug in the lower value. Oh, sorry. It starts off with plugging in the upper value first. Don't plug in the lower value first. So you got to plug in the upper value first into your antiderivative function. So notice how it's the same as this, except I plugged in 3. Then I'm going to subtract, and then I'm going to plug in the lower limit value. So it's always top minus bottom, basically. into my antiderivative formula function. That's me doing this part of the fundamental theorem. So notice that. Then what comes after that, y'all, is just simplification. So using some algebra, remembering PEMDAS, you would get 9/2 minus 1/2, which basically is 8/2. Well, hey, 8/2 is equal to 4. So the area of this trapezoid, everyone, is 4. And I did that without using geometry. I did that with antiderivatives. That is the key here. We did it with antiderivatives, and we're going to be doing it with antiderivatives because we're going to take up too much time if we try to do it with geometry. Let's see, does anyone have questions about this before we jump into you guys going in and trying it?
Yeah, I had a question.
Yes.
So the FB minus FA, can you repeat what that was again?
Yes, and this, okay, great, yes. So this FB minus F of A, so capital F represents antiderivative. And then when it says F of B, that is telling me that I need to plug in this B. So this is A, and this is B. My B in this case is 3. So notice how I basically plugged in my B, my 3 right here, into my antiderivative.
Oh, okay.
Yeah, and then the minus part, and then there's the F of A, so you're just plugging in that lower number at 1 into the antiderivative.
Okay, that makes sense.
Awesome. Yeah, great question. Let's see, are there any other questions coming up for us? You could unmute, or you could also, if you want to send a private message in the chat as well, whatever works for you all. So I'll pause here to see if any more questions are coming up for us. If not, we could jump into examples. Okay, cool. And if questions come up, feel free to, ask me. I'm happy to help out. Let me clear up my drawing. So yeah, I know it's like the sub video that was so last minute. So of course, it's like I definitely was anticipating coming back to this. So I'm gonna go ahead and move us. And I see 8 folks with us. If you're missing, I definitely want you to get your credit to move us along. But this is what I saw the other day. So let me go to the student view first. So first off, you're asked to find the integral. And I asked, show your steps. So I meant show your steps. And then I wanted you to sketch what the corresponding area would look like in your graph. Now let's take a look at what some of you had done. And 1, 2, 3, 4. 4 students had done this. So I'm going to give opportunity. I really like, so either Herman's looks great. I mean, this one also, I like the fact that they're imagining it's like the Desmos where you're using those lines. Awesome. And it looks like they were calculating, they were trying to kind of calculate this using geometry, right? This particular student. Then we have Pierre. I mean, I love it. So it's correctly shading the correct area, which is awesome. So we know how to shade what area this is representing. So that's cool. But let me look at the work. So take a look. So Gregory here, right, did it with geometry. So actually what I'm asking you, or I'm pushing you to do, is to try to use antiderivative to prove that area. So Gregory got 10, right? So Gregory got 10 for the area. But I actually see another Sophie Pickard, right here. They used the antiderivative. Notice that. They plugged in the upper limit value, which was 5, right? And then they minus and they plugged in the lower limit value. They went ahead and simplified and they got 12. So this is a correct application of the fundamental theorem of calculus. You're using antiderivatives. So I see Pierre de Fermat right here also used the antiderivative method. And Fan Chung down here started to use that. I think there was a conversion of decimals. Whatever helps. If you want to keep it as decimals, go ahead. Try and see if you also get 12, because I do see 12 coming up. So I wonder why Gregory got 10. So let me go ahead and give you all some time to finish up your sketch. So try this out.
Hi, I had a question.
Yeah, go ahead.
So I see the graphs, but I see that some of them start at 1 and some of them start at 0. Which one's right?
That is a good question. So how to tell which is which? I mean, well, first off, let me see if anyone knows that. So start at 0, because I see what you're saying. I see like this here, Dana's graph is shading and it looks like a full triangle, correct? And then we see Herman's graph starts at 1, goes to 5. This one starts at 0, goes to 5. Which one is right?
Mm-hmm.
Question. So first, let me see if anyone knows who is correct. So we have Dana or Hernan. And can you explain why? Okay, so Edgar says Dana. Can you explain either by typing it or unmuting why is, sorry, you said Dana is right or wrong? My bad. Okay, so Edgar says Dana is right. Can you explain to us why you think Dana is right? Either by typing or anything. And anyone else is open to, you could jump in. So Dana's graph looks like this, by the way, y'all. Okay, so I have a private chat. The integral goes from 1 to 5. It says because the bottom number is 1, so it starts at 1 and ends at 5. Okay, so Edgar, I see what you're saying, but does Dana start at 1? If you look here at the shading, does that start at 1 or 0 though? Is Dana right or wrong? Oh, okay. So Edgar, you're saying, so then we're saying that this graph is shaded incorrectly because you were saying the bottom number is 1. That tells us to start at 1 and the upper number is 5. And I also got a private message that says the integral goes from 1 to 5. So to answer your question, Roxana, so it should start at 1. So my feedback would be for Dana, you want to shade this way and then just, scratch off the parts before that. So it starts at 1 because the lower limit starts at 1 down here. I just call that the lower limit number. There we go. So that is an amazingly great question. Thank you for asking it. Area. So thank you, Pierre de Fermat. You shaded your area. So our goal is to find the area of that. But our goal is going to be that because this wave, I'm sorry, this parabola is curvy. It is curvy. That means it does not have sharp corners. We cannot use geometry. Like, yeah, you could use Riemann sums, but that's going to give you an estimate. We're going to have to use the fundamental theorem here. So we're gonna have to, because these are not two triangles, y'all. This is like that would be a curvy hypotenuse, and that's hard to take into account. Now, you can use geometry to approximate, like, yes, like perhaps let's say in the AP exam, it's multiple choice and you try to approximate, you could kind of get close to the answer. But our goal here, our learning goal is we wanna connect areas under curve with antiderivative. There is a deep connection with that. So let's go ahead and see what we have here. So I see 5x squared, and I see that we're plugging in the upper limit value. See, I see 2 being plugged in, subtract, and I see the same expression, but we're plugging in the lower value. However, I see, it looks like Doris here has a different antiderivative that they're plugging into. So I see a 4. And I see that they're plugging in the lower limit and subtracting the upper limit. So remember, for Doris feedback, you actually want to plug in the top number first and then subtract by the lower number. So no, top first. Top always goes first. So you want to just adjust that. Yeah, because then you're getting a negative area. And thus, the area would be positive for this one. All right, so let's go ahead and see. Then we have Pierre de Fermat using 1/2. They're plugging in the upper and they're plugging in the lower. So I'm seeing the 1/2 x squared come up from the prior slides, right? That formula. Mary Jackson, however, I see the third power coming up. So Doris and Mary, they're getting this third power, and I'm wondering about that. Like, I see some of you have the third power. I see some of you have the second power. Let's talk about that. So let's talk about that. So To apply the fundamental theorem, oh, let me see the chat. Let's do this. Okay, step one, y'all. I'm doing fundamental theorem. So step one, I know usually it's great to have the formula right next to me, but step one, find the antiderivative. So I'm gonna bring this down. Now I'm gonna remember the antiderivative formula. It's x to the n plus one divided by n plus one. Okay, cool. The 5 is just going to be right in the front. So cool. There's your 5. Now this 2 is going to be added. You're going to add 1 to it. So it's going to be x to the third. And at the bottom, you're going to have divided by 3. So you could write it like this, or you could have wrote it like this. So 5/3 x to the third, whatever is nicer for you. Step one, antiderivative. Do y'all see how I found the antiderivative? Notice how I just kept the 5 in the front. I just kept it there, but I focused on taking the antiderivative of the variable. That's what I did. So step one, antiderivative. So that is where some students were getting that third power that we saw. That is where we're getting that third power. Now I didn't check to see the rest of it, but let's see if anyone has questions about what I just did in step one. Step one, find the antiderivative. You have this one or you have this one. I think I'm gonna use the second one. I don't really like the giant fraction. If you like giant fraction, that's okay. And then it says, I just noticed I did it wrong. I know we have to find like the derivative. Yeah, thanks, Rosa. So the opposite of the derivative, so antiderivative, that's correct, Rosa. So that is what we're gonna do. Now, I'm going to go ahead and let me just erase this because I don't like this one. And I'm just gonna use this. Actually, I'm gonna rewrite it. Type out step 2, so I have it right here. That's when you're gonna, so capital F, y'all, represents antiderivative. That's when you plug in the upper value, so B minus the lower value, capital F, which is A. And we're plugging in the lower and upper into the antiderivative. That's what this is telling us to do. That's what it represents, because capital F means antiderivative. So we're gonna plug in first 2. So we're gonna say, okay, 5/3, plug in 2 to the third power, minus, now we're going to plug in -1 into my antiderivative. 5/3, and we have -1, and then it's to the third. So that is, I know my steps are crooked, but here's my antiderivative. Here's my second step where I'm plugging in the upper value, subtracting, plugging the lower to the antiderivative. Now, if I do this math, it should be that it's going to give me the exact area under this curve that y'all shaded here. It should be, according to the math, according to the calculus. So all we got to do now is kind of simplify this with some algebra. So 2 to the third power, that is 8, right? 2 to the third power is, no. Yeah, 2 times 2 is 4, and so that's 8. 8 times 5 is 40. Then we got divided by 3. Let me know if anyone has questions. So I did, this is 8, 2 to the third is 8, times 5, I got 40, and then I brought down the divided by 3. Then we have -3 to the third power. So that's just -1 times -1, that's +1, times -1, that's again -1. So then that's gonna be minus 5/3 times -1. Basically, these two negatives right here is gonna turn positive. So it's gonna give us 40/3 plus 5/3. Sorry, y'all, I can't right below this for some reason. Not for some reason, it's, so it's gonna be a plus because of the double negative. And that's gonna give me 45/3. Now, by the way, you could actually convert all this to decimals if you'd like. what is 45 divided by 3? So actually, oh, what's in the chat? 15, really? Well, that's a very nice area. Oh, and why did you put 3 in the denominator? Is it because of the exponents? Like down here, this denominator? Like the initial time I found the antiderivative? Like why is this 3 down here? Or why did I put 3 down here? So this was, let me call this A, and let me call this B. So there was a question about why did I put 3? And is it because of the exponents? So do you mean this part A or this part B? Like the initial time I put divided by 3 or the second time you're seeing it happen down in the last steps? Let me know and then I could address it. And so Juan says we got 15. Wow, that's really nice. It's a nice area. Yeah, sorry for the messiness. And but I could already start telling why we got 3 here. I mean, if you want to know. So usually when it comes to the antiderivative, the rule is this. And let me write down the rule. I'll write it in blue over here. The rule is you do x to the n plus 1. So because this was a 2 right here, because this was a 2, so this is the rule. Sorry, let me finish writing down the rule. And because this is a 2, that's going to give me x to the 2 plus 1 divided by 2 plus 1. So usually what you're seeing is that it does, if that's what you were asking, it matches with the exponent. The denominator number is matching with the exponent when you're taking the antiderivative. And that's why we have a 3 here and then a 3 down there. So it became 3 when we used the antiderivative rule. Let me know if that helped. If not, I am happy to re-clarify. So our answer is 15, everyone. Can I see that we are making an adjustment in our work to see that if we understand that we should be getting an area 15. So the area under what we just shaded is 15. It's nice how it's a nice clean number despite the curves. Okay, so I see Sophie Pickard got 15. Doris did not get 15. So it looks like what Doris needs to do, I think the only difference was that I had it divided by 3 or something in the initial round, I think. And then the 4 needs to turn to a 5. Okay, awesome. Okay, and then for Pierre de Fermat used the old antiderivative formula that was for the prior function. So because we have a new function, you had to find a new antiderivative. So you want to just adjust that formula. So I don't know if this person is actually here today. All right, Vaughn Newman, awesome. All right, Dana, and then we have Mary. So we have those who are participating here. All right, y'all. So I'm going to go ahead and bring us back. I really appreciate these honest reflections. So again, we just like the fact that y'all, there was a sub the other day. So it was very hard for you to kind of like get to dig into the meaning of this without the opportunity to ask questions because I wasn't there. So we just encountered this basically. So you just had some exposure to this. And so it makes sense that you're going to have many questions and you still need more practice. Like we only had like 2, right? I did prepare some more to go over, but due to our timing today, of course, we're going to have to just continue to talk about this next week. But if you are curious, right, like if you need some more practice, I did have, like I had a Google form, but we could do that next time. Right here, sorry, slide number 6 on today's slide. I provide some more examples. So for those of you who are talking about like why the fractions are coming about and so forth, if you want to see some more examples, but these are, so on slide 6 and slide 7, if you're curious. But we could also go ahead and talk about it Monday so that we, understand a little bit more on how to do this. So how that works. Here's a picture of someone's solution on the Google form. I like the color coding. So notice their answer, they got 46. That's one student. Here's another sample. This student got 19.75. And so we got 46, we have 19.75. And let's see, I have another third sample. This particular student got 46.5. So actually there was a variety of answers. There wasn't actually a very common answer. So today, my hope is we're going to talk about this and see what is exactly the answer. So one thing though that I noticed when I'm looking at these different samples is that they all kind of have a similar things. Like I see the 2x to the 4th over 4. I see that even behind there. I know I put some pictures in front of it, but I see it here. I see 3 coming up. And then I see substituting. So I see that the processes are there. It's just that we need some help with the arithmetic, the in-between parts, to kind of get ourselves cleaned up is what we need to focus on. So let's do this problem. So here is the problem. I'm going to try to write it on the board. And what I'm going to do is also stop my share. So let me stop. So let me do, I know step 1 is like I originally did like color coding. So I guess I'll do bottom number green. Top number, I guess I'll do purple. Okay, step 1. So I mean, that's step 1, usually color code. Step 2, take the antiderivative of this. So we're gonna take the antiderivative of this. And how we're gonna do is we're gonna plus 1 divided by that same number, and we're gonna keep that 2 in the front. So the 2 stays. Let's go ahead and add 1. So 3 plus 1 is 4. Then we have to divide, and these numbers are usually the same. So as a reminder, the antiderivative rule is, now where can I place it? Where is the rule? There's the rule. So as a reminder, where you're taking the antiderivative, you just add 1 and divide it by that same exponent. So I'm just doing that very same thing. Now, due to the spacing, I'm gonna have to erase it because I had no space, but that's the rule. So that's what we're using. Now, for this last one where you just have 3, you have to imagine that there's an imaginary like x to the 0. So we're still going to add 1. So 0 plus 1 is 1. Divided by that very same exponent is just 1. So we don't usually write divided by 1 or x to the 1st power. So I'm going to go ahead and rewrite this as just 3x. And I noticed that all those samples had that. So step 1, I took the antiderivative. So here's my original, here's my antiderivative, step 1. Oh my gosh, there's like 18 things in the chat. I didn't see all this discussion. Oh, no, that's from the past. Okay, great. Okay, so cool. We took the antiderivative. Next step is we're gonna go ahead and plug in the top number first, subtract, and we're gonna plug in the bottom number. So let's do that. So for the first one, I'm gonna be using brackets to organize my work. I'm gonna plug in the 3. And actually, everyone, before I plug in, I just looked at something. So I saw this 2 and 4, and I know I could reduce that to ease my work. So it's like, why? Let's reduce the 2 over 4. Someone in the chat or someone in class, what does 2 divided by 4 reduce into? Who said it? 1/2. So that's gonna reduce to 1/2. I don't know if I heard Hecka mumbling under the thing, but yes. Right here, and for those at home, 2 divided by 4, you could change that to 1/2. So let's just ease our life. Okay. So that way, we're gonna have less numbers to work with. It's gonna be nicer. So now I'm gonna go ahead and use this antiderivative. I'm gonna first plug in 3, so let's do that. So it's gonna be 1/2. I plug in 3 to the 4th power. Plus, don't forget to plug in into the second x. 3 times 4. That's my first one. That's the purple number. You know what? Let me do the brackets in purple. So y'all can see that's the top number. And if any questions pop up in class or at home, let me know. I'm going to subtract. And now I'm going to plug in my lower limit, which is going to be 1. So let me switch my color to my green again. I'm going to be using green brackets. I'm excited to see what the answer is, y'all. This is actually the first time I'm doing it. So I don't know who's right. Let's see. So we're going to again do 1/2. I'm going to plug in my 1. And it's to the 4th power. And then I'm going to add 3, plug in 1. So here's our setup, which I saw many students, their samples look like this. But again, the question is, how do we like reduce this? All right, what in the world is 3 to the 4th power? I wonder. 40.5. Okay, actually there's some stuff in the chat happening. Let's see. So let's see what's going on. It says, wait, why is there a 4 in the 3 times 4? Why is the other one 4? Isn't it 3? I don't know. What y'all think? Y'all agree with the with the students in the chat? Y'all agree that this 4 right here should be a 3? That's supposed to be a 3. So I got yes. How about we got yes, yes? In agreement? Or we have a shrug, so maybe don't know. So yes, this is actually supposed to be a 3. So thank you for those at home. Yes, there should be a 3 because we're plugging in the 3, the upper limit, into the antiderivative right here. So yes, that should be a 3. And I actually am going to just do this. So for those who didn't see that, 3. And this is 1. These should be the same. There we go. Boom. So now, thank you so much, y'all. So now either if you're at home or if you're here with me, yeah. Thank you, Shannon, for trying to clarify about the reverse distribution, the reverse power rule there. So now for anyone at home or here, what's 3 to the 4th power? You feel free to use your phone, or, you know, if I know we don't have calculators. So what's 3 to the 4th? That's the one I probably need some. 81? Thank you. So this right here we have just found is 81. Great. This, I know it's 9. 1 to the 4th, that's just 1. So that's, you know, just 1. And then 3 times 1. Let's go ahead and simplify all this mess. 1/2 of 81. What is 1/2 of 81? I know that's going to be like a decimal. Or 81 divided by 2. 40.5. 40.5. Thank you so much. Then we have plus 9 right here. Let me just bring down those purple brackets. Subtract. 1/2 times 1 is just 1/2. Then we have plus 3 times 1. We could change this to a decimal too. So this is going to be, so 40.5 plus 9. Great. You don't have to, I mean, I just like to keep the brackets. 3 plus 1/2, we'll just say that's 3.5. That's fine. Now, what do y'all think we get when we do this subtraction? 46, perfect 46. I see nods. Let's see what at home, what do we think? Shannon also says 46. All right, y'all agree. The answer looks like it's 46. So it looked like whoever had the very nice color-coded solution, they had the 46. So awesome. And then if you're interested in looking at that color-coded one, it is on the slide. So we have now figured out what the actual solution is. So this is kind of like helps us with the precision. Let me know if there's any questions at home or in class for those in here. Feel free to put it in the chat. But yeah. What was that? Basically saying is that if you take the derivative of an integral, you get back your original equation. That's essentially what this is actually saying. That's what this is saying. If you take the derivative of, it's basically telling us that they undo each other. That's what this is telling us. So it's okay if you're getting a little bit mixed up with the details in between, but that's the main juice. That's the main essence of what fundamental theorem part 1 is telling us. And that's all we need to actually understand, just the main essence. You're not going to be asked to reapply this right here. So let's see if there's any questions about the main essence. Here's the main essence. Let me type it out. The derivative basically undoes the integral. That's just it. That's what you want to get from fundamental part 1. But if you are interested, like to extend your learning and so forth, you feel free to take a look and try to figure out why this is the case. You could definitely do that as well. So let's see if there's questions about just the main juice of this. And you could try it out, y'all. At home, if you take an integral and then you take the derivative, you'll see that they're going to go back and forth. So it's basically fundamental part 1. All right. And I'm just trying to see if there's anything popping up in the chat for us. Cool. So if there's nothing coming up from this, let me go ahead and take us to the next part. Let me clear my screen. Okay, everyone. So to kind of just make sure that you understand like what's the difference between part 1 and part 2, this is what you would see if you were in a textbook. This is what fundamental theorem part 1 looks like. Notice how there's that derivative symbol, there's your integral, and if you take the derivative of your integral, you get back your original function. So that's the main essence. And then you could go ahead and read the little details about this theorem and this version of the theorem. Part B, right? This one right here, this is fundamental theorem part 2. That's the calculation thing that we just did on the board. That one is actually finding exact areas under a curve. So go ahead and read this because we're going to be doing a Padlet. So take the time to read it, understanding just right now, even if you're not there yet with fully understanding. What do you think makes part 1 and part 2 different? Again, let me show you. This is part 1. Let me type it in to make sure y'all know which is part 1. This is part 1. Down here is part 2. What does that mean? Why did my external display disconnect to? Let's see. Part 1 is a new function for area under curve. B is finding the area under curve. Yeah, part 1 only gives the function to be able to get the area. Part 2 lets us plug in and get the actual area. And then thinking is showing us different steps for getting the area. So a lot of you are understanding that, integrals are used for area. We're getting that new function. I see that coming up. We have a few thoughts still developing there. And we have that new function coming up a lot. So that's like a common trend I'm seeing here, that part 1 is showing you a new function. But let me go ahead and reiterate what should distinguish these two things, everyone. So the difference between the two, I'm going to go ahead and use the annotation tool, but it's actually not popping up for me. So I'm going to go ahead and verbally do it. Let me guys go ahead and verbally say what's the difference between the two. For some reason, my annotation tool is not popping up at the moment, but the difference is, and let me go ahead and reiterate it. Part 1 is telling us that the derivative undoes the integral. That's what part 1 is telling us in that theorem. The derivative cancels out the integral. That's the main essence. Part 1 is just telling us that. Part 2, the one at the bottom, is giving you the steps to actually calculate area under curve. So part 1 is telling us derivative undoes integral. Part 2 is actually giving you the exact steps that you want to follow to find the exact area under a curve. So that is actually the difference between the two. Usually right now I'll be typing that out, but again, my little annotation tool disappeared at the moment from my screen. So there's where we're gonna land. So I'm gonna go ahead and take us back to our slide. And we're gonna go back down to number 11. Now, actually, I guess it looks like for folks that are here, so I don't know if it's helpful for me to project my screen. I'll ask you all after, but I'm gonna try to disconnect it. So let me see if my annotation tool pops back up. So I think I'm just using AirPlay is what's happening here. Oh, my bad. Someone said, can I repeat it one more time? So for the last one, sorry. Yeah, because I didn't type it right. So it makes it a little bit hard. So let me go back and repeat what I just said. Right here. So let me go ahead and finally type it out because now I can do that here. So part 1 tells us a derivative cancels out an integral. That's what part 1 is telling us. That's why at the end you get f of x, because the derivative cancels this out and you just get your function. Part 2 is basically giving you the steps. Oh, well, it's all in caps. To calculate the area under a curve. So that is the difference between the two. I went ahead and typed it out because it was requested that I repeat that. So there it is for us. I typed it right here and typed it down here. So that's the difference between the two. And for folks here, feel free to copy that down on your little copy. So it definitely helps to know the difference. Like you're hearing calculus, and this is the fundamental theorem. So this is what is calculus right here. And if you're able to explain the difference between the two, that's pretty advanced. You could explain that to, like, your friends, impress them. Okay, so let me go ahead and clear this up. And let's go now to this picture that y'all are so probably tired of seeing always. But I told you all at the beginning of our module that this right here holds the essence of the fundamental theorem of calculus. But why is that the case? That's
But I think part 2 is going to help you find the distance. I think that's on the straight or
which one, the distance?
yeah,
Accumulation.
which that's on the straight or accumulation graph.
Uh-huh.
But like part 2, like fits into that one. And for the first graph, it tells the derivative comes out in integral.
And hold on, and wait, sorry. So you got part 2 fits the accumulation, the distance one. And then what was the second part you said?
And then part 1 fits the speed over time. I don't know if it's right.
Speed over time, but not sure if right. That's okay. I went ahead and typed it into the chat for sure if right. Or it could be the other way around. So I went ahead and typed in an in-person thought about the connection with the fundamental theorem. So they had an idea that part 2 fits the accumulation part. That's this one here. So basically, like, distance is accumulating. That's your accumulation. This right here is a rate because it's speed. So saying that part 2 fits here. And then part 1 fits this here. But then not sure if that's correct, or it could be the other way around is what I got as an idea. So let's talk about that. So this is the essence. So this right here, if you're able to explain this, shows you do have like a strong hold on understanding on what we're doing and what is, calculus. So I'm going to go ahead and I'm going to show you once more the connection between the two and how this even relates. So I'm going to go ahead and once more begin this again. So as you know, I always keep doing this. I'm going to shade the area under the rate graph. And for those who are here, like, feel free, like, if you forget which one's rate and which one's accumulation, you should write it on top of it. So this right here is my rate graph that I'm shading. And if you find, or if you calculate the area under the rate graph, if you find the area of this rate graph, so that's going to be base times height. So then now we're saying, part 2. Let's find the area. So if someone's thinking about part 2 already, because remember part 2 gives you exact steps to find area, love it. When we find the area of this, we get the accumulation, which is the distance. So let me just type that out. Area of the rate graph gives you accumulation, AKA distance. And then remember there was a way that this distance graph relates to the rate graph. And how it was so is because if we actually take the slope, so 150 divided by 3, that's our slope of this graph. If we do 150 divided by 3, you should get 50. And that is your constant rate over here, your speed. So then I'm going to put the slope of the accumulation graph gives you the rate, which is your speed in this case. So that's how these two are connected. And now let's talk about how it's connected to the fundamental theorem. So basically, fundamental theorem is basically this, y'all. The area under rate graph, y'all, that is your, let me change my color. That is taking the integral. So if I take the integral, I get my area. That's what the symbol means. That's the elongated S. If I take the integral of a rate graph, I'm going to get my accumulation. It's crazy. And then slope. Now, what's slope mean again? If y'all remember, taking the slope of something is actually a derivative. So slope is actually you taking the derivative of the integral to get back your original function. Because remember, this right here gave you the integral, your accumulation. But if you take the derivative of your integral, you get back your original. Isn't that crazy how it's all connected? That's why I'm saying this right here holds the essence of the fundamental theorem of calculus. So let's see if there's questions on that. So there's your connections. Remember, integral means you're taking the area. And when we take the area, you get your accumulation. But if you take the derivative or if you take the slope of this accumulation, these cancel out and you're going to get back your original. So that is like a visual kind of expression of the fundamental theorem. Let's see if there's anything coming up for us in the chat or in person, if there's any questions.
So the rate graph is part 1 and the accumulation graph is part 2?
Actually, so there's a little comment there, it's in private, but it's actually like both. It's a little bit of expressing both, not exactly just one. So for example, you know, down there when I'm going this way, I see part 1 where the derivative undoes the integral down there. And when I'm looking at this, I see part 2. So like taking the area into the curve, you're going to get some number. I see part 2 on top and I see part 1 at the bottom. But a student says it's like part 1 and part 2. I also think that could be right too. But yeah, so that's awesome. You're all already thinking about like which is part 1 and which is part 2. And you know, I can't, oh, that's why, it's because I'm annotating. So yeah, so that's my answer to those. Let me know if anyone has any clarifying questions about this. I know I can't get rid of my little chat box. There you go. Okay, cool. So I don't see any questions coming up at home or here in the class. I'm going to go ahead and clear this up. I think it's really cool, the visual representation and connection and how long we took to build this up. We're finally getting some answers. Now it's your turn. So in your own words now, describe how the fundamental theorem of calculus is related to that essential question. And we're going to go back into the Padlet. So I'm going to once more put this in the chat. Now, I went ahead and described that. I drew pictures and, you know, we had some clarifications, there were some questions. But now let's see how you understand it. So in your own words, let me make sure this to everybody. We're gonna go back in the Padlet. We're gonna go to that next column. Describe the fundamental theorem of, how the fundamental theorem of calculus is related to this original essential question that you were asked. How are rate graphs and accumulation graphs related? Basically, it's what I just did in the board. So go ahead and just kind of rephrase your understanding of what you understood from that. And if anyone at home has any questions or clarifications about what you're being asked to do, let me know. But we're on column number 11 right now. Let's take a minute or two. And again, put your name or initial there for your credit. Mm-hmm. I know some of you are still adding in your comments, but I'm going to go ahead and take a look at what our thoughts are in here our last 2 minutes. So let's take a look. Wow. So there's a lot of connections. Again, some of you are, I see a lot of resonance on what's going on here. I highlighted the RG in purple here because I like how simply it was stated. The simplicity, the shortness, the conciseness. The area of the rate graph gives you accumulation, aka integral. Sorry, I added that, or the integral. And the accumulation graph gives you, so I would say that's ddx or the derivative. So I like the conciseness of it. But if you all are interested in a more thorough kind of explanation, check out JL's, just in case if you're struggling like at home. But otherwise, everyone's thoughts are definitely on point. So as our checkout today, let's just think about this column number 11. And for those at home, please finish up. For those in here, y'all are free to start packing up. It was an awesome first day. Thanks so much for the tech help, y'all. But yeah, so awesome. Make sure you finish this for those at home, everyone. I'm gonna go ahead and stop my share. I'll be giving credit for today's stuff.